Welcome back to Tailored Materials and Surfaces. Today we're going to think about measurement systems for surfaces. So I've just written a list. It's a relatively random list. I've just chosen some of the more common techniques and some of the ones that we happen to have. It doesn't mean they're the only ones. One of the things that we might want to know is the surface energy. It's an important measure because that would determine how easy it is to stick things like paint or adhesive onto our surface. So we might want to measure the contact energy somehow. Typical ways would be some form of contact angle by putting a drop of liquid on the surface, or by CFM, by chemical force microscopy, by coming up with a probe, with some kind of sticky probe, sticking it on the surface and measuring how easy it is to pull it back off. That can be either done on a macroscopic scale or on a microscopic scale using an atomic force microbalance microscope. XPS, my students are familiar with, so that's X-ray photoelectron spectroscopy. It's a type of spectroscopy where we shoot in an X-ray and we get an electron out, and we can measure what elements are in the surface of our material. It goes down a few nanometers, maybe tens of nanometers, not much further. That is sometimes surface sensitive enough, sometimes it isn't. Sometimes it's too surface sensitive, we only see the surface, but usually it's good enough. Sometimes we would like to just see the surface. To see just the surface, we would use something like TOF-SIMS, which is time of flight secondary ion mass spectroscopy, where we measure actual atoms in the surface. We knock them out and measure their mass. Going a little bit more simple in physics, but difficult to use, infrared can be used for surfaces. We need to use it in such a way that we don't send our infrared too deep into the surface, because the infrared is typically long wavelength, so it will penetrate very deeply into our sample. And if it goes right in and we don't get it back out, there's a problem with working out what we want to measure. So typically we would have some sample that we want to measure the surface of, and we don't want our infrared going right inside. We would use a low angle reflection or an internal reflection and ATR method for doing that. And I connected that later on in this talk to SNOM, which is near field microscopy, which uses a similar principle, that if we have if we're very close to an optical component, it doesn't behave like normal physics. It starts to do quantum mechanics, and we can make it smaller than, or we can measure smaller things than we would normally be able to measure with light due to diffraction. Then we get on to two techniques that we actually have at our laboratories: quartz crystal microbalances, which use an oscillating piece of quartz to measure mass effectively, or at least something related to mass. They're very sensitive. They don't tell you what is causing the mass, whereas these other techniques tell you what the atoms are, or in this case, what the elements are. This tells you what the clusters are. This tells you what the functional groups are. Infrared tells us functional groups, but not atoms. Surface energy is less specific, but we might only want to know that. Quartz crystal microbalance tells us also less specifically what mass is on there, but that might be what we want to know. So we can tell how quickly we're putting something on, or if we're doing a corona discharge, how quickly we're removing material. EIS is electrochemical impedance spectroscopy. It only works if our samples are conducting, but it can be also used to investigate surfaces very effectively, because the function of AC electricity is often confined very close to surfaces. If we have surfaces going on, they will affect the signal that we get here. It's difficult to interpret, but it's comparatively easy to set up, which is why it still exists. I will talk about these for a while. I've actually already done it because I lost this introduction bit, So we will go back in time for me and go over them. So if we look at a drop on a surface, this will be a drop of liquid on a surface cut through at an angle, sorry about the blurriness. If we have a point at the edge, the liquid can't support forces laterally. It can support forces vertically because it's stuck to the surface, but it can't support forces laterally because what's going to stop it moving? So these forces in the flat plane have to be balanced in some way. The forces on the edge of the drop. This force here is the surface tension of the liquid. This force here is the surface tension of the solid. And this force here is the interfacial tension of the liquid and solid, just to have all of the forces. And if we add them all up, we should get to 0 in plane. Vertically, we might not. So we need to take the part of this force, the surface tension force, that is in plane. So moving over here for a little bit, we have the possible forces. Oh, it makes my arm go weird again. We have the possible forces, so we've got the tension of the solid liquid pulling in this direction, the tension of the liquid vapor multiplied by the cosine of the angle, because that is the length of this side. It's the cosine of this angle, because this is what the surface tension is pointing in, or it's pointing in this direction. But if we take cosine and we have it less than 90 degrees, it will be positive, and if we have it more than 90 degrees, it will be negative, and so we get the correct direction. It changes direction when it passes through 90, that's good. And then we have the liquid vapor force in the other direction. So popping back over this side, checking my microphone as well, and turning off some software that's popped up on my screen. So, try again. So, popping back over to this side, we can make an equation that says all of the forces added together equals 0. We've got one in one direction, one in the other direction, and the one multiplied by the cosine that could be in either direction and is smaller than the total value. We can then move this one, which is the one we want to know, because theta is our unknown, or theta is something that we can know. We can move these to the other side, and that gives us two difficult to measure things that we would like to know: the solid vapor interfacial tension and the solid liquid interfacial tension, because we're trying to measure the surface energy. So we really want to know the difference between these two. So if we leave these on this side, that tells us exactly what we want to know. So let's put these over the other side. So that gives us this form, and we can also move this gamma LV below our two terms on this side, although it's not strictly necessary. It depends what we're trying to measure. Practically, it's easy to measure the surface tension of a liquid, or easy-ish. We can look them up in tables because they've all been measured. It's practically difficult to measure these two, but we can determine the difference between the two, which is useful. And if we use different liquids and we know the value of the surface tension, we can get more information about it from how this behaves when we change this. It doesn't tell us the absolute values, but it tells us how energetic the surface is, and is often used as a quick measure. The more a drop spreads out, the higher the surface energy of the surface is. But getting the actual value out of it is not quite so easy. CFM, chemical force microscopy, is much the same. We take our atomic force microscope, we attach something to the surface, maybe some OH molecules, something that ends in OH. So using our tailored materials and surfaces, we tether something to the surface that has an OH on it. We approach our surface and we measure how much effort it is to remove it from the surface at that place. And then we can move it to another place and measure the force there. We can then do exactly the same as with our contact angle. We can change the chemistry, so we can then put on a hydrocarbon, for example. which can only interact with non-polar interactions, and measure the interaction strength then. Obviously, we will have to take multiple measurements, just as with contact angle, to remove any factors like roughness that will interfere with our measurement. Maybe the softness of the surface will also cause trouble. If we measure a range of liquids or contact surfaces, then we will be able to extract some kind of information on the surface energy. Okay, moving on to XPS, or X-ray photoelectron spectroscopy. It's a measurement which my students are somewhat familiar with. We shoot in an X-ray, knock out an electron from an atom, a core electron, and we measure its energy, because due to quantum mechanics, the atom is forced, it must absorb all of the energy of the photon, and it then has to do something very quickly. It spits out this electron, so the electron energy is equal to the X-ray energy minus the energy of this orbital, because it has to knock it out of the orbital and it's lower than an electron in free space. We get a spectrum and we can compare it to elements, so we can get an idea as to which elements we've just hit, and we get some information as to what they're connected to, because this electron energy is shifted slightly depending on how it's bonded. It tells us more about the oxidation state than it does to exactly what it's bonded to. So it is difficult to tell the difference between some things, and it's very difficult to see very light elements. Things like hydrogen don't appear because they don't have an extra electron, and very light elements have little signal. But heavier elements are easy to see. What is important here, however, is our surface effect. So this only penetrates a few tens of nanometers, or actually more importantly, the electron can only escape a few tens of nanometers. And depending on the angle that we use to shoot it in, if we have a flat surface, we can control the angle by tilting our sample. We can reduce its effective distance by increasing the distance that it goes, that the X-ray goes. It increases the distance that the electron has to escape through, and that means we get more surface sensitivity. Next technique is TOFSIMS, or time of flight secondary ion mass spectroscopy. So it's a type of mass spectroscopy. What is a secondary ion? Well, we have to have a primary ion to have a secondary ion. So we shoot in an ion onto our sample, we knock out another ion, so we generate another ion, and we measure its mass spectrum. Looking at normal mass spectroscopy, we need to have a charged, plane flying over, sorry about that. We need to have a charge on our species that we want to measure so that we can measure its mass. Let's have a look at that. So if we take a sort of any old mass spectrometer, we need an ion. It's got some kind of mass. Let's start off at Earth potential so that we know what it is, but it typically won't be. We will then accelerate it by 1,000 volts. The distance doesn't matter because the further apart it is, the lower the field, so the force is lower and the distance is longer. If it's shorter, the distance is shorter, but the force is higher. So the work that we do, the force, that is the momentum that we give to this ion, is the same. If it's a light ion, it will be going very fast because we're applying the force on the charge. If it's a heavy ion, it won't be going nearly as fast, but it will have the same energy. And that means that we'll have a spread of speeds when we get out of here. In a traditional detector, we would have two charged plates. They would be curved, and we would allow our ions to go through them. Some of them would be curved towards our detector, and some of them would crash into the side. Some of them would be curved too much and crash into the other side, so we could have a tube coming through here to our detector and change the voltage to allow the correct ions to pass. So we could scan the voltage and allow different ions to pass. What we see is that the radius here of curvature is also dependent on the mass and the velocity, but there's this squared term in here, so we can still sort out the different velocity ions even though both things are dependent on mass and velocity, because one of them is squared. That allows us to separate heavy ions from light ions in this process, but that is not the time of flight. Time of flight takes into account the fact that they're all moving at different velocities. So if we start off a whole bunch of ions at one point of time and catch them after a long path of travel, whoops, sorry, my head is all Bart Simpsoned, catch them after a long path, then we will be able to use the time of flight and not the bending in a magnetic field to separate them. So this tells us some things that our time of flight spectrometer has to have. It has to have ions that all start at the same time. So we need sorry, my thing looks like a W. We need a source of ions, or of a way of making ions from our sample that generates them all at once and then stops. We need a standard accelerator, and we need to get rid of any other ions and not neutral species, and then we need some long pathway, and then we need a detector that's very fast, because the detector has to know exactly when the ions arrive, and obviously they're going pretty fast. So they're not going to take very long in a practical length piece of tube. Remember, this has to be all in vacuum, so it becomes relatively quickly impractical to have a very, very long tube. And they're going straight, because if we bend them, then we have the same problem. Our tube would have to be very, very wide if we bend it, because how are we going to move them without discriminating between different speeds? So it needs to be straight. So this brings us back to the nitrogen ion gun that we had last time. So if we have a source of nitrogen, a gas cylinder, and we have some electrodes in here to light a plasma, we obviously need to control the pressure, so we'd have to pump it out at different parts. And then we set up an acceleration. In this case, we're going to accelerate negative ions. So we're going to have a positive electrode at the front to accelerate the negative ions, and they go out through a hole, and then they're going to hit our surface. What we can do is we can switch this voltage, or we can switch a shutter very fast, so that we have little bits, pulses of nitrogen ions that come out and whack into our sample. That would be our question mark. When they hit our sample, they are then free to move away. So that would be our nitrogen ions coming off, and also our unknown. Let's have a question mark ion coming off. That might be positive or negative. It's been molested by these ions, so it's now got some charge usually. It might not have any charge, but the ones that have no charge won't get seen. Then we can attract those to our starting gate, effectively. So we want to attract them into the spectrometer, into the time of flight part of our spectrometer that we just had. So then let's have that. So this would be the time of flight part. Obviously we have to accelerate them first, so let's have that. So acceleration section, and then the time of flight part, and then the detector. This obviously raises a problem, because if we shoot nitrogen in there, we won't know where the nitrogen came from, whether it came from our surface, our sample here, oops, give it some thickness, or whether it came from the nitrogen gun. So typically we don't use nitrogen. These devices often use relatively uncommon elements. So one that I know of uses gallium, they use cesium, they use things that we're less likely to find in our surface, something pure, so that we know when we get it that that is our gun iron, and then we can measure. This is particularly good for measuring surface because we're going to just knock off the surface atoms. This is a very weak technique. If we turn the voltage down here, we don't drill holes into our sample, so we're only going to measure the surface, which is what we're interested in this particular case. If we measure the surface, we can knock off atoms, we can knock off little clusters of atoms, we can knock off parts of molecules, and they go into our time of flight and get weighed. They will be sometimes doubly and triply charged, but because we can very, very accurately determine the time of flight, we can determine the mass to charge ratio of our particles, we can then use a computer to extract a lot of information from that. So if we have a simple molecule like polyethylene, we will get a very large number of peaks from it, but the ratio of those peaks and the ratio of isotopes in those elements are fixed, mostly fixed, and we can use that to extract information on what it is. So if it's a polymer made from carbon, we can use the ratio between carbon 12 and carbon 13, carbon 14, to tell us some information. So every peak, every methyl peak, contains several sub-peaks, satellites of higher mass from the carbon 13 and carbon 14, and also of deuterium. Those aren't very common, but if the peak is big enough, we can see them. If it's a metal, it will have isotopes. If it's chlorine, for example, we will see the two isotopes very clearly. Usually we make positive ions, but there is nothing stopping us from measuring negative ions with this too. So if we want to measure something like fluorine, fluorine atoms very, very rarely can be measured as positive ions. They're a lot easier to measure as negative ions because they capture an electron here in this plasma and then leave as a negative ion. So we can typically switch the field on the entrance of our time of flight device so that we can measure positive or negative ions. We can't do them both at once. So this technique is particularly sensitive, particularly surface sensitive. It only goes a few atoms into the surface. It doesn't damage the surface very much at all. It is actually knocking off atoms from our surface and sucking them into our spectrometer, but we're counting them individually, so we don't need very many. And that means that our sample is barely damaged by this. It's less damaged than if we scratch it with a cloth. It does mean it's very difficult to prepare the sample beforehand, because if it's dirty, if we've touched it with a fingerprint, all we will see is fingerprint. So the next topic would be infrared spectroscopy. Because infrared is relatively long wavelength, it's getting on for micrometers. It's a little bit shorter than micrometers, but it's getting on for micrometers. If we shoot it perpendicularly into our surface, then it will penetrate very deeply. That was a bit of dust flying around, sorry about that. If we don't do that, but we run it at a very low angle, then we will get grazing angle infrared, so we can have a reflection spectrum. And because infrared has a long wavelength, it doesn't notice that our surface is not very polished. So we don't need to have a very shiny surface. We do have to have a very shiny surface for visible light, because the visible light is interacting with small things on a hundreds of nanometer scale. Infrared is bigger, and so it doesn't see scratches, particularly at a very low angle. At a very low angle, most things are incredibly shiny and reflective for infrared. An alternative, and a good alternative, is ATR, which is fully written out as attenuated total reflection, and we will look into that a little bit to see what's going on. So if we have let me draw it now properly. So if we imagine a piece of infrared transparent material that's behaving like a prism, we shoot our infrared in here, it reflects off the inside surface and bounces back. It's very much the same as it would inside an optical prism, inside a visible light prism, inside a optical fiber. Let's zoom in on that and see what really happens though. So if we have a very low angle of incidence, our light will reflect very well and it won't escape very much. But if we get up to just where there's total internal reflection, so we choose our angle carefully to be the Brewster angle, just where we get total internal reflection, then some of the light actually looks out. Quantum mechanically, we've got effectively a barrier that the light is tunneling through. It doesn't turn around completely, but we can see here we've got this wave, and the wave has to bounce here and reflect and go back the other way, oops, this way. And while it does that, there is a little bit of light that looks out of our interface. So each wave that comes along, each photon that comes along, looks out a little bit, part of a wavelength, into the other medium. If we had an optical fiber, we would typically coat the optical fiber to stop that from interacting with anything outside. If we've got an ATR in our infrared device, we are deliberately using that to measure things. It's very practically useful. So in the one that I have, we have a diamond with one bounce. So it's just doing one reflection, and it's a diamond. The good thing about diamond is it's hard and it's chemically resistant. So we can put things on the top here and measure them. We measure almost only the surface because this light can't escape. Well, it can escape, but if it escapes, we won't see it because we're measuring with our detector this beam. So this is going in, this is coming out. We're measuring with our detector this beam here. That's very handy, but it brings us also to our other topic that I wrote there, the SNOM, or it's got another name, I'll look it up. So why mention a SNOM? We don't have one. They're relatively rare, but the physics behind them is much the same. So let us think about it at this point. If we take an optical fiber and we sharpen it to a point, so we pull it out to a point and coat the outside so the light can't escape, we shine light down it, even if the light wavelength is longer than the width of the hole, it can still escape. When it gets outside, it will diffract immediately. So if we draw where the light goes, it ends up going a long distance outside. So this is where my light would shine to. But if I move very, very close to it, that's why it's called near field optics. So this would be near field scanning optical microscopy or scanning near field optical microscopy. There is a little bit of intensity of light here, which is incredibly bright. So our light goes in, most of the light ends up here, it then diffracts and spreads out everywhere, but before it's managed to diffract, all of the light is available in this little cone. So if we move our sample very close into this bright patch, then we can measure things that are smaller than the diffraction limit of light, that are smaller than the wavelength of the light that we're using to look at them, which is really handy. We then have to move this peak around, this fiber around, to measure our surface, and it takes a very long time, which is why they're comparatively rare. They're typically an accessory for an atomic force microscope, because then you have all of the parts that are required to bring something very, very close to a surface without crashing into it, and to steer it around. So typically it would be an accessory. The next flavor technique is quartz crystal microbalance, which is a piece of piezoelectric material. It's the same as is in a quartz clock. I'll click this pen again. If we apply a positive voltage to one side and a negative voltage to the other side, It distorts. Let's draw it distorting like that. It distorts in this fashion. So it moves one face across the other. If we apply an AC voltage, it starts to oscillate. The interesting thing about these is that they have a fundamental frequency, so they have a frequency they like to oscillate at, where one wave of a sound effectively fits inside the crystal. That's okay, then that is why they're used for timing devices in computers and clocks, because this frequency is relatively exact, much more exact than normal electronics can be, and then it can be used to count, to keep things on time. A typical quartz crystal microbalance would be running at a few megahertz, somewhere between 5 and 20. And when we add something to the surface, so let's add some material to the surface, it will slow it down. We can derive a formula relatively easily for how much it gets slowed down. I won't do that right now, you can do it yourself. I'll put it in the notes. But if we add material to it, it behaves like the quartz getting thicker and changes the frequency. So if we can measure the resonance frequency of our quartz, we can measure something to do with the added material. If it behaves itself very well, we can measure the mass of the added material and guesstimate the thickness, and we can get down to sub-monolayers. We can measure less than a monolayer, less than a full layer of material depositing. These are very often used in coating machines to grossly measure, just find out what's going on, because they will measure up to tens of nanometers of thickness, but they will also measure right down to a sub-monolayer. So the last technique in our rush through surface techniques would be electrical impedance spectroscopy. So this is where we vary the frequency, because it's spectroscopy, we vary the frequency of an electrical signal and measure how difficult it is, how much energy is lost. What does that mean? Well, let's do it with a circuit first. So if we take our impedance spectroscopy or our impedance spectrometer and we add it to a simple circuit that has a capacitor and a resistor in it. If we take a frequency of 0, so DC, we will charge this capacitor up. So let's make this plus and this one minus. We charge the capacitor up and then current will stop. So we measure an impedance, a resistance of infinity at 0 hertz. If we measure at infinity hertz, effectively, we will never charge the capacitor up, and so we measure just this resistance. Left the resistor in there, so we measure a resistance. So we've got measure this resistance at infinity, or at high frequency, and we measure the capacitor, or we push through, we measure the capacitor as a break in our circuit at very low frequency, and depending on how we connect our devices up, so we could put the resistor in parallel instead, and that would change how it charges up. So if we use our electrochemical impedance spectrometer to measure an electrical circuit, we can deduce a lot about it, what the components are. But we don't want to use it for that, we want to use it for measuring surfaces. So let's imagine our aluminium oxide that's been anodized onto the surface of a piece of aluminium. So we've got a thick layer of aluminium oxide with pores in, and we've left them open. If we take 2 of these, it makes life simpler because we don't have to worry about what the other one is. So we can connect 2 of them to our 2 terminals and use them against each other. We probably should have a reference electrode in there so that it doesn't get electrolyzed, but aluminium oxide is quite stable. If we do this, we can identify some electrical components in here. So we've got our ions, whatever we want. Let's have SO4, 2 minuses, and sodiums, A pluses, and they've got to move around to carry current, so they're in water. And they can move around, but they in the solution relatively easily, but that will have a resistance, but it's not a very big one, R. So that will have a resistance. But this piece here will have a much higher resistance because the ions have to go down these narrow channels. So this is a higher resistance. That's what we will then see. This piece here is a non-conductor, so it will behave like a capacitor. So we will see something very much in our aluminium, very much like the circuit that we had beforehand with a capacitor and a resistor. This resistor is very low, so we can either discount it or we can add it to this one. It might be difficult to tell the difference. If we had two different aluminium samples, then we would have two different capacitances and resistances in our circuit, and we would end up with two different frequencies when it would switch between conducting through the capacitor and not conducting through the capacitor. And we could identify those. It's hard to tell which is which because they're not labeled. We would get a spectrum of impedance, let's call it, because I haven't given it a name yet, and frequency. Let's call it F in Y. So F, and it will go down, won't it? So it will go down in 2 steps, we would imagine. We'll get some kind of curve like that. Our impedance spectrometer has some software which we can use to extract information on what the approximately is going on. The difficulty, as I said at the beginning, or I might have forgotten because I had to record this twice, the difficulty with this technique is usually in analyzing the data without making too many assumptions. It's relatively easy to do it with aluminium and aluminium oxide because we can form a thin layer of aluminium oxide and we can grow it thicker and thicker. So we've got comparison specimens. But if we've got something unusual, then it's difficult to see anything. Okay, I'm going to have to stop there because it's late. This video took longer than I expected to, and I've accidentally lost a few bits that I'm going to have to record again. So I'm going to leave it at that. It was just a race through techniques. I will put more onto our course website, and I will make videos on the individual things in the future. Maybe not for this course, but at another time.